Okay. Talking back through this, for those of you who, for the recording. E equals V over D. That's an equation you already given. Electrical field strength equals the voltage divided by the distance away. Okay, so I substituted in the equation for electrical field strength. Not the F over Q idea, because that's a little q that deals with the charge getting pushed around. I dealt with the big Q, the guy doing the pushing, just because then I can get some distances to cancel out. That was kind of my end goal, to get to an equation that was simple, not more complex. All right, so I substituted in ED equals V. E is KQ over R squared multiplied by the distance, right, which is R. One of the R's cancels out, gives me this base equation right here. KQ over R is the voltage. Now, this is how you would determine what voltages to put around some big charge. Say it's positive right there. This equation is what you would use to determine what voltages and what points there are out in space. Remember, we solved a whole bunch of problems where I said, you know, I've got 30 volts here and 15 volts here, and I have a proton, and I allow the proton to, you know, move from 30 to the 15. How much kinetic energy does it pick up, or what's the final velocity? I worked the problem just like that, and I pulled the 30 and the 15 just out of thin air. Okay? Well, you don't just have to pull this out of thin air. This is the equation that we give you. Okay? All right, back on this. Now, back on this. Where are the voltages coming from? They're coming from this equation, right? This idea of the proton moving. Well, why? How do these voltages come about? Well, the voltages come about because you got a large positive or negative charge, and so then at certain distances away, there is a voltage or a potential energy per unit charge. That was the other definition of voltage, right? So here, if you will, just as a an easy example problem, I've got a 3.2 coulomb charge. Okay, I have a 3.2 coulomb charge. At a distance of, I don't know, let's go 1.5 meters. What is the voltage? Notice this is dealing with, and let's make that a positive 3.2 coulomb. This is dealing with a large charge that would be pushing something else. Okay, a large charge that would end up pushing something else. Okay. So I mean, this is a flow chart. V equals KQ over R, not R squared anymore. R squared for electrical field strength. R squared for Coulomb's law, K, Q1, Q2 over R squared equals the force. Okay? Not for voltage. R squared is no longer, it's R, which shouldn't be that big of a deal as long as you hear it, try to keep it straight in your brain, and please write it down correctly on your equation sheet. Okay? So this is flow jug. V equals K times 3.2 over 1.5. Remember, K is 8.99 times 10 to the 9th. Please plug that into your calculator. This should come out somewhere on the order of to the 9th, approximately.
To the 10th.
To the 10th, that's fine. What does it come out to, Gabby? 1.9 times 10 to the 10th? Units here. Yes. Volts. Volts. Units here will be volts. The units for voltage is the volt. Now, volts, we're all cool in physics. We use slang and lingo. The idea of volts is actually a short term in slang in our cool physics world, as sad as that is. The technical idea here would be electromotive force. Okay, but I'm going to get to EMF. I'm going to get to all of that other idea later on. Okay, whenever we do circuits. So we're not there yet. For now, voltage is just voltage, it's just volts, and the unit of voltage is volts. Okay. So you get just that simple. Plug chug style problems. Okay. Now, let me take a little bit of time and let's try to set up all the equations that we've gone through, kind of like the core ones that you would need to use a lot, okay? And make a difference between the things that you would need on your equation sheet, okay? Now, we started out at the very beginning with Coulomb's law, force K, Q1, Q2 over R squared. And we didn't really worry about this one's bigger than that one, or this charge is pushing this guy, because it's the force between two charges. Both of them will be pushing on each other, okay? Equal and opposite forces, Newton's third law. Coulomb's law. So we're not worrying about which one's bigger, which one's getting off the field, which one's getting pushed in the field. It's just Newton's third law. Remember, equal and opposite forces. If you figure out the charge from Q1 on Q2, that's the exact, or excuse me, figure out the force from Q1 on Q2 using this guy, that's the exact same force as from Q2 on Q1. Because does it matter mathematically to do Q1 times Q2 or Q2 times Q1? No, right? So whenever you do the triangle problems and you have to solve for all the charges around, remember if you solve for one of them, you already got the force for the other ones. You just got to change the names. Okay? I'll look back at your homework if you're trying to remember that. Now, then I defined, then I came over here for electrical fields, and I said, now an electrical field is defined as E equals F over little q. An electrical field, or the electrical field strength, is defined as the force that a small positive test charge would feel. Right? Force per unit charge. The amount of force per unit of charge that a small positive test charge would feel. Okay? So it's F over little q, or the force divided by the little charge getting pushed around. Okay? Whoever's getting pushed around at that point. But it's also, if you don't have a little charge at a location, let's say, that's getting pushed by an electric field, they just say there's this charge here. What is the electrical field strength caused by this charge at such distance away? Well, if you plug in Coulomb's law for F, you get K, and we used big Q here to indicate the big charge that's putting out the electric field. Technically, all charges put out electric field. But the big Q, the guy doing the pushing, if you will, the big guy putting out the electric field. Okay? I've got a charge or multiple charges. Right? What is the electrical field strength caused by these charges off in some location? Okay? The difference between when you want to use these different equations. If you have an electrical field, you're told an electrical field, or you're not told the electrical field, but you're told this force is applied to this charge, right? That's little guy getting pushed around. I don't care if the little guy is technically big, right? If you know a force is getting applied to a charge and you're asked the electrical field strength, top, E equals F over Q, right? The force being applied to the charge at that location. Okay. Or maybe vice versa, right? There's an electrical field strength, or there's an electrical field, E, and some charge Q is placed in the electrical field, and when a charge is placed in an electrical field, it goes flying. It gets pushed around. It's the little guy getting pushed around. That'll allow you to calculate the force. Now, this guy down here, this guy will heavily be used for if you don't know of a charge at some location in an electrical field that's getting pushed around. You don't know anything about somebody being pushed. There's not a charge at the location you're looking for. It's just an X off in space, something like that. But you have a couple or one or three, however many, big charges. Each of them puts out their own electrical field according to this equation. Electrical field equals K times that big charge, putting it out divided by the distance to that X off in space squared. Okay, it's a vector, right? So you get an angle from the shade of the angles that I give you, and you add those vectors to get the net electrical field. Okay? More or less.
If you're not given force, and you're looking for
Correct. Correct. You're not given a force, or you're not given an electrical field. Okay. I like to think of this as big guys bullies, if you will, putting out an electrical field or pushing somebody. Use bottom equation. Little guy thrown in an electrical field that gets pushed. Top equation. Okay? Somebody is getting pushed, someone is getting moved. Top one, someone is doing the moving. Bottom one, big Q, little q. Okay? Then, from this idea of voltage, we got this equation. Work equals negative Q delta V. Right? Work, the amount of work that a particle does is equal to negative charge of particle times the change in potential difference it goes through. And I'm purposefully using, once again, little q. Because generally, whenever we're talking about this is a small charge you are pushing through, or it is flying through some voltage, right? It's the proton that we push closer, we do work on and we push closer to some other large positive charge. Or it's the proton that comes near the other positive charge and I release it, and it picks up speed as it goes away. Remember that the work is the same thing as kinetic energy, right? Change in kinetic energy. And so over here, with the W, you can go in change in kinetic energy, which becomes 1/2 mv final squared plus 1/2 or minus 1/2 mv initial squared, and the initial velocity is almost always 0. It cancels out, but it can be 1/2 mv finals squared equals your negative Q delta V. You have problems like that in physics. Yes. Think just like you did with conservation of energy. Think what is happening here. Am I pushing this thing and doing work on it, right? Or am I releasing it and it's picking up speed, right? It's gaining kinetic energy. If it's gaining kinetic energy, then you use change in kinetic energy. Is it coming in with some fast speed, like opposite the direction it would want to go, and the electrical field or the change in voltage, if you will, is slowing it down, right? That's starting fast and getting slower. That's a change in kinetic energy, right? If you see anything about a changing velocity, changing speed, kinetic energy. Okay, kinetic energy. And then today, I gave you this idea. This is allowing you to see how much work or how much is done on a little charge when applied to such voltage. How do you know what voltages are coming out from this thing? Well, a voltage is KQ over R. Okay, the voltage at some location away from a purposefully big Q here, the voltage at some point away from some very large charge is equal to K big Q over not R squared, just R, the distance. Okay. So those are the basic equations you will need on your equation sheets.
Sure.